Record. All right, my name is Matt Fleming. I work at the Hydrologic Engineering Center. I've worked on with the HMS team here for 20 years this June, so it's gone by really fast. I've had the opportunity to work on testing, code development, model applications, training, and just general tech support. So I've had the opportunity to do all those things over the past 20 years, and it's been a real pleasure. And then David Ho, David's a newer member to the HMS team, or newer to HEC in general. He joined, I think 2 years ago now.
2 years, yeah.
David. All right, good. 2 years, he came from the Sacramento District Corps of Engineers, where I believe, how many years were you at the Sacramento District, David?
About 10. Yeah,
About
with
10
okay.
All right. And if you don't mind, just give a little background for the type of applications or work that you're familiar with.
Yeah. So I also help out with in addition to helping out with the math section, the hydrology and statistics, I also help out with the water resource systems division. And there I help out with the HMS and the integration into the HEC WAT program. So if anyone's familiar with that HEC software, I help with just trying to make sure that that it integrates well into there, doing testing there, and also application of using HMS in the WAT. And also in addition, supporting the HMS section with testing and getting a little bit into the code development.
Right. Thank you, David. And David's helping with questions today. So if you have a really hard question, he would appreciate it. The harder, the better. If you can stump David, then that's worth extra points today. Yeah. All right. And Jacob, I'll give you a chance. Is there anything you want to say to the group before we get going?
No, I think I'm just other than I'm looking forward to hearing it. I mean, I think that I know HMS as a whole, I think it's used somewhat inconsistently, I'll say, across our throughout the different states, because I know like some states I talk to, they have a lot of experience, and others, not so much. But I think that it's a very I recognize it's a very dynamic and dynamic tool and a lot of capabilities, and I just think we can learn a lot and do a lot with it, and I look forward to learning more about it. And yeah, just again, thank you, and yeah, that's all I got.
All right. Thank you. Let's get started. Yeah, no. Feel a little bit awkward too. I'm used to 2 monitors in the office, and today I'm working from home, and I have just 1 monitor in front of me, so it's a little challenging, but I think we're getting used to it, right? We're getting used to working at home or working in the office right now, and so just doing the best with what we have. I was a little nervous because on both Monday and Tuesday, there's been big IT failures. WebEx wasn't working yesterday from 9 to 9:30, so I was having a panic moment. So hopefully we make it today. All right, so this presentation is about HMS, and I'm going to start with just some basic information first. So here's the outline. So just background for HMS. Go over documentation that's available to everybody. Tech support that's available to everybody. So the HMS team, we provide most of our support to the Army Corps of Engineers. Those are our primary customers. But we do have agreements with others to provide support. Uh-oh. Can you still see me? Okay. And then we also have a new avenue, and I'll show that in a minute, where anybody can ask questions and we can post those questions for anyone to see. So it's really cool. Other tech transfer tools that we're working on or that we're utilizing. And then I'll go over just some basic terminology with HMS that we all on the same page about. And then go over new features that you all should know about. So the HMS team has released, 5, 6 versions in the last 2 years, and there's been tons of new features in those versions. So there's a few that I really want to point out and highlight for you all, and then of course questions later on. All right, so we're on the same page. Here's a screenshot of the HMS webpage. So this is part of the HEC website. And for downloads, this page is already, or this image is already stale. HMS 4.10 Beta 2 was released on Friday. So if you want to see the latest version and the latest features, you can download Beta 2, 4.10 Beta 2. And you don't have to have administrative privileges to install. So what we do is we have a Windows version, which does require administrative privileges, but then we also have what we call a portable version. And you can download the portable version to your computer, unzip it with 7-zip, and then you can simply run HMS by double-clicking on the HEC-HMS.exe file. So that's the way that we're trying to deliver versions faster to our customers and not have to go through the hassle of getting their IT involved to install the software. So the portable versions have been fantastic. So yeah, latest release was 4.9 that was made a couple of months ago or weeks ago. And then we also have versions of HMS for the Mac OS and Linux operating systems. So if anybody is interested in those, you can go to the same webpage that you see here, scroll down, and then you'll see a little block of text for Mac OS and then Linux as well. Documentation. This has been a huge change recently. I'd say in the last 3 years, we've transitioned from creating our documentation in Microsoft Word and then going through a huge review process and then converting it to PDF and posting it to our website. Now, most of the HMS documentation and most of the documentation at HEC in general, it's web-based. And so we're able to log into our development system, go to different pages, make changes, so add new text or edit text. And once we hit the commit button, that new information is made available to the public instantly. So this has been a much better workflow. And now all of the developers, they can add documentation as those new features are being created. So that's really exciting. You'll notice if you go to the HMS documentation page, you'll see release notes for each version. And so we try to have just a little bit of verbiage right there that shows these are the new features or these are the new bug fixes. And then if you want more information, you can go into the actual user's manual itself. The technical reference manual, it's a little bit stale, but we're working on updating that over time. We have an application guide that shows different applications of HMS. A validation guide that you can show, or the validation guide is really there to give you all comfort, right? It's there to show that we have tested different components of the software, different algorithms, and we have verified that the results are as expected. So that's the reason for the validation guide. And then at the bottom there's the link to the HMS documentation page. All right. Tech support. So this is what I was mentioning earlier. So this is the opportunity for anybody to submit a question to the HMS team. We'll post that question, or we'll answer it there in Discourse so that anyone can see. I believe at the moment, though, let me back up just a little bit. At the moment, only Corps of Engineers people can submit the question. But what we're doing is if we get any in the HEC-HMS inbox, what we do is we take that question and answer, and then we post it over here too. So that's kind of the workflow right now. In the future, anyone should be able to sign up for an account and then post the question here into what we call our Discourse page. And so you can see on this image, someone that was asking, is there a file size limit for DEMs being processed in HMS, so for terrain models? And so you'll see verbiage there at the bottom, going through best practices, right? So for watershed and reach delineation, do you need a really high resolution terrain model for that type of application? And then on to tech transfer. One of the new avenues that the team is trying to relay information to the field is through the use of tutorials and guides. And these are meant to be kind of short hands-on workshops. So you'll see at the top of the tutorial or guide, you can download the example project. And then there's probably a list of steps in there so that you can follow along and try to apply the same workflow that the tutorial is describing. And you should be able to add that information to the model, run the simulation, look at the results, and just really understand that new feature or that specific capability that the workshop is trying to highlight. And so if you go to the tutorials and guides page, you should see, oh man, there's probably 50 to 75 tutorials out there highlighting different components of the software. So those are exciting. And then videos too. So also on the technology transfer link, there's a link to one of our classes that we had last March. And you can go to that link. You should be able to click on any of the videos. It should take you to YouTube and you can watch. We tried to make them short. A few of them are a little bit longer. We did our best for our first try, but you should be able to watch those videos and see just some basic information about use of certain components of the software. And then you can also download the PowerPoint files that were used to create those videos. And then also, I think some of you are on the HMS mail. Well, you get the HMS emails from the HMS team. And so you should get those notifications that we have quarterly webinars. We do those to the Corps of Engineers, but we then also open them up to anybody that's on the HMS user list as well. So if you're interested in those and you're not seeing those webinar invites, just send me an email, or you can go to the HMS webpage and there's some directions there to get added to the email list. But we do those webinars, and then we also do webinars to the field, to other district offices, and then we'll post those to our webinar page. And so, for example, today, this webinar, after it finishes processing, I'll get it into YouTube, and then I'll add this webinar to that same page, that same tech transfer page. And then I know a lot of folks from the NRCS said that they were not going to make it today, and could they please get a link to the webinar? And so what I'll do is it'll be on that page, and anybody can watch the video as their time permits. All right. Yep, that's just the image showing the COP HHNC, so the Hydrology and Hydraulics Community of Practice webinar series that we do at the Corps of Engineers. All right, so moving on. So now we're going to talk about basics, so just some basic terminology with HMS. And hopefully that'll help us get on the same page as we talk through the new features after that. And again, if you have any questions, post them there in the chat. And David or myself, we'll get to them as we can. All right, so HMS. So what is the hydrologic modeling system used for? So HMS is what I refer to as a precipitation runoff model. So you provide meteorologic boundary conditions, so precipitation, solar radiation to compute evaporation, transpiration, temperature for snowmelt computations, and so on. So it's a precipitation runoff model. So you have those meteorologic boundary conditions. And then within the basin model, you have options to model different hydrologic processes on the land surface. So you can model infiltration into the soil, canopy interception, surface depression storage. You can also simulate base flow and then the transform of direct runoff or excess precipitation to direct runoff, channel routing, simple reservoir simulation. So you have those capabilities within HMS. And then HMS has different modeling methods. Like I mentioned, some are empirically based, like the initial and constant or deficit and constant loss method, conceptual or physically based. We have different physically based modeling options like the green and amped method, where those model parameters are based on physical information in the watershed, like the soil type or like the land use conditions. So you have different modeling options for different types of applications. And then you have different ways to represent the watershed too. So in this example, I have this watershed. Let's say it's 200 square miles. You could represent that entire watershed with one subbasin, and you could average your model parameters for that entire drainage area. You could subdivide that watershed into 3 smaller subbasins and then average the watershed characteristics and meteorologic boundary conditions over just those 3 subbasins. So that's another opportunity. Or you could go to a discretized representation where within each of those subbasins, you could apply gridded meteorology. So you could have gridded precipitation, apply that to the basin model. And then there's different modeling methods even in these scenarios where if you want to do gridded loss computations and cell-to-cell routing, you could do that. Or you could choose to apply the gridded precipitation, but then convert that to a basin average and then have basin average loss computations and then using unit hydrograph to transform direct runoff to the watershed outlet. So tons of different options you get to choose based on the modeling application and of course your budget, right? So if your budget doesn't permit you to delineate 1 square mile watersheds for a large watershed area, then don't do it. You can keep the model simple for the level of application that you need to perform. All right, HMS can be used for both event and continuous simulation. So if you want to model just one precipitation event where evaporation and transpiration really don't impact the computed flow, then you can do that. And that's what you see on this figure on the left. So it's a shortish, about a 7-day duration event. So you have one precipitation event early on, then you have about 24 hours of no rainfall, and then another precipitation event that really drives the flood hydrograph. You can model scenarios like this. If continuous simulation is important, then you could run, so we have in this example right here, about a 60-year period of record, 60 plus. So if you did want to do continuous simulation, include evaporation, include simple reservoir operations, then you could do that within HMS as well. And then HMS is both, it could be used in deterministic or I'll say an uncertainty mode. So HMS, you can define one set of model parameters, click the compute button, and for sure expect that each time you click the compute button, you should see the same hydrograph, right? There's no variability in the model parameters. So every time you hit compute, you should see the same hydrograph. So that's the deterministic compute. There is an uncertainty analysis option. So if you do have some uncertainty in your model parameters, so maybe you're uncertain in the initial conditions, or you're uncertain in how excess precipitation is transformed into direct runoff, then you could input that uncertainty information and run HMS in an uncertainty mode and see the variability or the range in computed flow. So you have those types of options in the software as well. And then we'll touch more on this when I go through the new capabilities that you all should know about. So GIS processing. This is really exciting. This is, in my opinion, a real game changer in HMS. So no longer do we have to rely on other software to delineate watersheds for us. We can do this directly in HMS. So there's tools, GIS processing tools that allow you to process a terrain model and come up with a delineation, a subbasin and reach delineation. And so these capabilities are directly built into HMS. You can also compute your subbasin and reach characteristics. So your longest flow path, your basin centroid, slope along the longest flow path, all those capabilities are in HMS as well. And then the next area that we're putting more and more emphasis into, parameter estimation. So if you have GIS data sets, your curve number data set or land use, soil types, those types of information, you can load those into the project and HMS will process those GIS data sets for you and compute initial subbasin and reach parameters. All right, some terminology here. All right, so on the left, this is what I call the Watershed Explorer, just Explorer. This is just like our Windows Explorer or File Explorer, right? You have access to all the model components here in the Watershed Explorer. So you should be able to get to your basin model, your meteorologic model, your control specifications, and then time series, gridded data, temperature data, and terrain data. Each of those major model components lives within its own folder structure. That's the Watershed Explorer. And then if you click on one of these components in the Watershed Explorer, you should see in the bottom left what I call the component editor. That should change for each of these major model components. This is where you're going to go to enter certain information for that model component. For example, I have the meteorologic model selected right here in my Watershed Explorer. And then in the component editor down here in the lower left, I'm able to specify the precipitation method, the temperature method, the evapotranspiration method, and so on. All right. The Watershed Explorer and the component editor, those are going to be linked to one another based on what is selected.
Oh, here it is. Okay.
All right.
You talked me through it. Thanks.
All right, just another reminder, if you have a live mic and start talking, we're going to hear you. All right, and then in the basin model area here, I referred to whenever you open up a basin model, if you click on the basin model in the Watershed Explorer, you should see it in the basin model map area. And this is where you get to see if you have background maps or you have your model components, you can interact with those your basin model components here in the basin model map. Right? And then the bottom portion of the screen, this is what I call the message window. This is where you're going to see notes, warnings, and the dreaded error messages if those pop up. And hopefully the information or the description there is good and point you in the right direction. But if you don't understand what the error message is, you can always post that to, or send us an email, or we'll eventually let you post it to the discourse page that I mentioned. And then at the top, we have our menu options. So those are our major menus that you can choose from. And then different toolbars. We have just the basic file structure toolbar, different modeling elements in the basin model, the simulation toolbar, and then the newest toolbar is our spatial results. And I'll talk more about spatial results in just a minute. So that's the basic user interface. The last thing I forgot to mention, within the Watershed Explorer, you should notice 3 tabs right here. So the Components tab, these are those major components that I just mentioned. And then also you have access to the Compute tab and the Results tab. The Compute tab is going to show you all the different simulations that you have configured in the project, so you can have access to those. And then the Results tab gives you access to the results from the different simulations. You have different ways of accessing results. You can access those from the Results tab, or you can access them from the basin model map as well. For the basin model, you don't have to go the geo-referenced route. You don't have to load in shapefiles or terrain data. You can always create a very simple basin model by dragging and dropping the icons. So probably most of you, if you've used HMS recently, you're familiar with this approach, right? This is the basic approach. You click on a subbasin, you drop a subbasin in the basin model map. And you can drop other elements. You would configure those or connect them to form your hydrologic network, and then parameterize and then run a simulation. So that's the easiest way to create a basin model map. If you do go that route, though, you don't get to use or take advantage of some of the spatial components that we have in HMS anymore. You're not able to apply gridded precipitation or view spatial results if you go that route, but it's still an option. We're still supporting the non-geo-referenced modeling applications because those can be really fast. All right, and then the geo-referenced basin model, right? So now if you do have those elements, those subbasins and reaches that have geographic information associated with them, then you can start doing things like applying gridded precipitation, or you can start seeing how the storm or how the excess rainfall varied across the simulation time window using maps across the basin model. So those are some of the strengths. Also, there's different ways to interact with the basin model. If the elements are geo-referenced, then instead of just interacting with those element icons that we're used to, you can interact with your polygons. So you can turn off the element icons and interact just with the subbasin polygons, and then just with the reach polylines too. So there's different ways of interacting with those elements in the basin model. That was the basin model. Let's jump to the meteorologic model. And as I mentioned, so the meteorologic model is used to compute the boundary conditions for the basin model. So it's going to be used to compute precipitation, temperature, evapotranspiration potential. And then currently with version 4.9, it computes the snowmelt as well. So the output from snowmelt is going to be your liquid water at the soil surface. But the team is busy right now working on a transition from 4.9 to 4.10, where snowmelt is being moved to the basin model. So after that move, the MET model is going to be simplified a little bit, where it just focuses on precipitation, temperature, and evapotranspiration. And then within the meteorologic model, you have different options, right? You have different options for how you want to model precipitation. If you do want to link in gridded precipitation from different sources, you can do gridded precipitation. Or if you want to set up a hypothetical storm like well, I'll go over the hypothetical storm in just a minute. The frequency storm, or if you have your own gauge weights or a specified hydrograph, there's just different options out there for modeling precipitation across the watershed. And then simulations. I'm sure most of you that have used HMS, you're probably the most familiar with our basic simulation run type. The simulation run is where you combine your basin model, your meteorologic model, and then the control specifications that tells the simulation start on this date, end on this date, and use this simulation time step. All right, so that's the basic, the simulation run. But then there's a ton of other options too. There's an optimization trial. So if you have observed flow and you want the program to automatically adjust certain model parameters to improve the fit between the model and the observed flow, then you can use the optimization trial. There's also a forecast alternative. This is designed for the water management folks within the Corps of Engineers. Depth area analysis, that's a simulation that's powerful for your hypothetical storms or your frequency storms, where you want to compute the frequency flow at multiple locations in the watershed. The depth area analysis will automatically adjust the precipitation depth based on the drainage area and your area reduction factor for each of those points in the basin model. So it's a really powerful tool that should save time if you have multiple locations where you want flow frequency information. Then there's the uncertainty analysis compute that I mentioned, where you're able to define or select different model parameters in the basin model or the meteorologic model, and the program will adjust those for you in a Monte Carlo type simulation. And then the newest simulation type, the frequency analysis, what that allows you to do is it allows you to combine or really aggregate different simulations that combine basin models and either the hypothetical or frequency storm meteorologic model. It will run those different simulations and compute a flow frequency curve for you, which is really neat. Just a second. There. All right. And then I mentioned this in the simulation run. So this is, again, it combines the meteorologic model, basin model, and the control specifications. This is the simulation type that most people are going to be familiar with, or most people are going to use. And you're going to see results like this. You're going to see for a subbasin element, you'll see a hydrograph, a flow hydrograph. You'll see the base flow. You'll see your precipitation hydrograph at the top. And you'll see the differences between the total precipitation and then the precipitation loss is in red there. So you'll get that type of information for a subbasin element. There's other types of results from a simulation run. You should be able to see a global summary table. So for each of the elements in the basin model, you'll see a table that shows the drainage area, the peak discharge, time of peak, and the total runoff volume at that location. That's the global summary table. We have a new summary table for metrics, your model metrics. So for locations that have observed flow, you'll be able to see a table that shows for those locations, the root mean square error, the Nash-Sutcliffe efficiency, percent bias. This is the percent bias and runoff volume, and the R-squared metric. So it's a nice table to summarize model performance at locations with observed flow. You'll see the hydrograph plot that I mentioned a few minutes ago, and then also the summary table. This is just basic summary information where you'll see the volume of runoff for that location, the time of peak runoff, the peak runoff value, and then compare that to any of the observed flow information as well. And then finally, spatial results. So we have a figure here that shows, this is a new type of capability. I believe it was released in version 4.7, but it's steadily being improved here. If you turn on spatial results for the simulation, then you'll be able to see plots like this for precipitation, precipitation excess, loss, snow, 2D flow output, and other types of variables. That's really neat there. And then also within those spatial results, if you click anywhere in the map on top of that spatial result, you'll see a time series plot, kind of like this one. So this shows the snow water equivalent for one of these grid cells here in the modeling domain. So you can see how that snow water equivalent changed in time during the simulation. And then also the model metrics. I showed you that table where you can see model metrics at different locations in a table view. You can also see those model metrics in the basin model map as well. We're going to display those for you graphically. And you can see for those subbasins where, in this one, we're looking at the Nash-Sutcliffe efficiency. For those subbasins where it's green, we have a Nash-Sutcliffe efficiency between 0.8 and 1. So those are the areas where modelers should have some confidence in their model results. And then you can see for the yellow and reddish areas, maybe those areas need a little more calibration to improve the model results. But this capability is available in that beta version that's on the website at the current time. And then finally, the team is working on this. This should be released in a future 4.10 beta release. If you want to export a static TIFF image of any of those spatial results, you can export that. Or if you want to create an animation and export that animation, that capability should be available as well. All right, and then almost done here with the basics. So 6 ways to access results in HMS. My favorite way to access results is to make sure the simulation is selected here in the simulation toolbar. Choose an element in my basin model map. So I'm going to choose this junction right here, and then click the graph button. Right, if you click that graph button, then you'll see a plot for that one element right there. So that's one area. The other way to get results is you can go to the Results tab of the Watershed Explorer. You can expand the tree for each of your simulations. So I've expanded the tree for the water year 2011 simulation right here. And then for this element, I expanded the tree even more to see the different types of time series for that element. At the top of the list, that's the default graph. So that's just the basic sub-basin plot that shows you precipitation and flow. But if you want more time series results, you should be able to click on each of these different types of time series and then see a preview plot, or you can click this plot button as well and see a larger plot for those selected time series, right? So you can click on one of these. You can click on precipitation, hold down the control key, click on air temperature, and once both of those are selected, choose the plot button to see a bigger plot of those two results. Let's see, the animation toolbar for spatial results, we talked about that. And then also reports. Reports are a newer option to HMS. I believe those were added maybe back in version 4.5, but within the last couple of years. The reports, they're going to show you input parameters in the basin model, and then for locations that have observed flow, you'll be able to see computed and observed flow information as well. All right, I'll pause there. Let's see if there's any questions about the basics before moving on. Let's see. So yeah, if you want to ask a question, go ahead and unmute yourself and you can ask the question. Or if you just want to put it in the chat, that works as well.
Stuff? You mean how many times?
All right, looks like we just had one question come in here.
Give me a second. I'm gonna find it. Give me a second.
Somebody has a hot mic. Let's see. It's not asking a question. Got it. All right, so gridded data. So HMS supports various types of gridded data. Yep, so there's a new import option in HMS. If you go to File, Import, there's a gridded data import option, and you can import gridded precipitation, you can import gridded temperature, you name it, your gridded model parameters, you can import that information and use it. There's tons of tutorials out there. Let me just show you for a minute. I think this is worth stopping. All right. So I'm going to go to the HMS documentation page here. Under tutorials and guides, click that link. And then if you find the, there we go, working with gridded boundary condition data. If you click that link, you're going to see about, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different tutorials walking through how to import gridded data into HMS or manipulate the gridded data as well. So there's tools that allow you to improve the information from one grid set with information from a different grid set. So that's the normalizer utility that you see right here, which is a nice tool to incorporate maybe your daily volumes from Prism into the radar rainfall hourly volumes. So that's a nice feature. And you can click on any of these links here. So this one right here is probably the best. So importing and using the MRMS, the multi-radar, multi-sensor precipitation data. So there's some information where to download the gridded data, and then it's going to walk you to using the import gridded data wizard to load that into the HMS project and use it. All right. Any other questions out there?
I did have a question, Matt. In regard to the GIS, I guess, features or functions there, once you have your projections set, are there base maps or anything that are linked to the the GIS part of the tool? I couldn't remember.
There's not yet,
okay.
But we build a list of questions or input from the user community, and getting those base maps added is something that we want to do. So we're just waiting on like the right time when we can get to it. But yeah, we want to add aerial imagery and other types of background maps. So there is a nice little R&D initiative within the Corps of Engineers to add the capability to directly import terrain data from the USGS. In a future version of HMS, you should be able to identify your area of interest. Maybe that's with a watershed boundary, and then it should automatically go to the USGS National Elevation Data Set, clip that information, project it, maybe resample it, and then load that into your project for you. So that's one of those really exciting features that I'm looking forward to.
Absolutely, very cool. All right, thank you.
Yep. All right. All right. Thanks, David. I see you got the link in there. All right. Well, let's keep going. Yeah, and I should have said this earlier. Sometimes when I start talking, it's hard to realize that there's other important things too. So if you need to take a break, take a break. We're recording this. You can always pick up where you left off or check out what you missed. But yeah, take a break. After I finish the next 20 or so slides, then I'll give all of us like a 10-minute break, and then I'll start the demo. If you can wait about 30 more minutes, go for it. But if you need a break now, go ahead and take the break.
Hey, Matt, how will you be sharing this, the recording?
Yeah, that's a good question. All right. So what I'll do is after I get the MP4, whatever the video format file is, I need to load it into our YouTube channel. And then what I'll do is on the webinars page right here, I'm going to add another row that describes this webinar, and then I'll put a link in here on the right side so that you can just click on the link and it should open up in YouTube for you. All right?
Yep, thank you.
Yeah, there we go. Yeah, this page is slow sometimes. But yeah, you can see from some of the past webinars. So the JPAC did one recently about the new sediment and debris flow capabilities in HMS. So you could see that one. You can just click on that link and it should start for you. Well, of course, after you watch a commercial. All right. All right, let me keep going. All right, so new features that you all should know about. All right, so here's the list of features that we want to go into, just a little more description about the GIS delineation, GIS characteristics, and parameterization. Hopefully, you'll find those as useful and beneficial as I do. Then we'll talk about the hypothetical storm. If you used HMS maybe 4 years ago, maybe 5 years ago, we didn't have the hypothetical storm. Back then, we had the SCS storm. What we decided to do is to generalize it, make it more just ready for future enhancements, right? So now we call it the hypothetical storm, and there's many more user options now. And we'll go through all of those user options. You can still treat it like the SCS storm. If you're interested in the SCS temporal patterns, you can still choose those 4 to 5 temporal patterns if you want to. I'll touch on the reporting option that's available, and then the PMP optimization option that we have in HMS. And then I've already talked about online documentation, but if we have any more questions or comments about where to find certain things, then of course we can review those as well. All right, the GIS tools, yay. This is my favorite. And the reason why this is my favorite is for the first 15 years of my career, I supported HEC Geo-HMS. And I was the person that would interact with Esri. I think Esri's great, but we wanted to move in a different direction with our GIS tools. We wanted to have more control, more flexibility, right? And then develop tools that are really specific to application of HMS. And so we were utilizing the TAL DEM GIS library for delineation. And then there's other GIS libraries that we're utilizing as well. The take-home message is we're not recreating a GIS library. We're not reinventing the wheel. We're using available GIS tools and code to do the delineation, the parameterization, the characteristic options in HMS. As part of the GIS delineation process, you're going to run through the tools that you see here on the GIS menu. So you're going to run through those. If you're familiar with Geo-HMS, do you remember how many menus that you had in Geo-HMS? Put it in the chat if you remember. I'll pause just a second, but there's more than one. Oh, maybe you all were lucky enough not to have to use it. But if you did, if you used HEC Geo-HMS, you would have, oh man, probably about 7 different menus to run through. And each of those menus had 4 to 5, maybe more options that you would have to click through. And it was a very sequential process, right? You'd have to click on this and then click on that, and then just run through all of those to get to the end product. And if you look at how just short the process is here in HMS, to get to a delineated model, you really have to go through just these top 7 items, right? So it's much more streamlined than it was in the past, which is great. It's great for getting a model up and running. Also, there's the tools like I mentioned, computing your physical characteristics of subbasins and reaches, and then tools are underdeveloped and available right now for estimating your model parameters. All right. And if you understand the information on this slide, then you understand how the automated delineation process works, right? So the Tau DEM library, it follows the same type of approach that Geo-HMS used, right? So we have our 8 pour point model. Water's going to flow in the direction of the steepest slope from cell to cell. And so what I have right here, this is my terrain model. Each of those values represent an elevation. Right, so if you look at these values, these elevation values, you can get an idea for where's the steepest slope, right? For this upper left cell has a value of 78, we'll just say 78 feet. The steepest slope is going to be in this direction right here. So we're flowing from 78 down to 67, right? When the water flows in that direction, the flow direction code is a 4, and that's where you see this 4 right here. This 4 indicates water is flowing from this cell diagonally to the right to that cell right there. All right. So water flows in the direction of the steepest slope. Looks like I've highlighted this value right here of 46. If we look at the neighboring elevations, this guy right here, 37, there's the biggest differential in elevations in this diagonal left direction, but the flow path length is a little bit longer from the centroid of this cell to its diagonal neighbor. The flow path length is actually shorter from 46 to 38. Water is going to flow in that direction. That's your steepest slope. And then what that means is that cell, the cell that has the value of 46, is going to be assigned a flow code of 5, right? Water is moving from 46 to 38, right? That's how flow direction is computed generally in HMS. And then also, once we know the flow direction, once we know the direction water is moving, we can start accumulating how many upstream cells there are from a given cell, right? Let's go back to our example where water is flowing from 78 to 67 in this diagonal right direction. So we know that this cell right here, that my 67 cell, only one cell is upstream of that location. So it has a flow accumulation of 1. This cell right here, my 53, there's 3 upstream cells. If we look over here at where the lines are, you can see this cell is flowing into it, this one, and that one. So that's where we get a value of 3 upstream cells. If we know the count, or how many upstream cells there are, then we can get a drainage area for each of these points, because we know the area of each of my grid cells. Let's just assume that they're a 30 meter by 30 meter grid cell. If we know the area of each grid cell, then we know the drainage area at each of these flow accumulation cells. And that's the basic process for how delineation works right there. Water moves in the direction of the steepest slope. And then the next step is, well, let's say we want to define reaches. We're going to set our stream threshold in this example to 3. So anything that's 3 or more, that's part of my stream network, right? And what you can see in this figure right here, these red lines, they indicate where the stream network would be drawn in HMS if the stream threshold was set to 3 cells, right? Once you define that stream threshold, then the next step is going to be the automated delineation process. And what HMS does is it takes those identified streams and then it creates a subbasin for each of the tributaries. And the question I have here is, how many subbasins and reaches would be delineated if the stream threshold was set to 3 cells? All right. Well, let's look at it. We can have this one subbasin right here because we get to a junction. And what that means is this tributary is going to have its own subbasin. So it's these cells that flow on this tributary this tributary right here. There's one subbasin. Then we're going to have a separate subbasin for this tributary here. And then we're going to have one more subbasin for this local area, or the area downstream of that junction. Right? So if your stream threshold was set to 3 in this very simple example, then you're going to walk away with 3 subbasin elements. And then you would have one reach element. The reach element, since these are headwater subbasins, even though the identified stream is identified inside the subbasin, HMS is not going to represent this with a reach element. It's going to only represent this area right here as a subbasin element. The same for this area. This would be represented as a subbasin element. And then downstream of this point is where the program would use a reach element to route the flow from these 2 subbasins downstream. Okay. All right. The first step in the GIS delineation process is you have to define the coordinate system. What I like to do now is, instead of going in there and just going through the menu to define the coordinate system, what my workflow is, I'm going to load my terrain model into HMS. Well, before I do, I'm going to make sure I know the projection of the terrain model, and I'm going to make sure that projection is something that I want to use, right? So if it's unprojected, if it's geographic coordinates, I'm not going to use that. I'm going to project it into something like UTM, or the standard projection that the Corps uses is Albers equal area feet. So I would reproject the terrain into that type of projection. And then I would load that terrain into my HMS project and then associate that terrain with my basin model. And once you associate a terrain with your basin model, then HMS is going to ask you if you want to set the basin model projection to the terrain's projection. And that's my usual workflow right there. Right, we have a question here. So is there a rule of thumb for selecting the threshold for the number of subbasins? Ooh, I like that. Let's hold off on answering that until we get to the demo. So Jane, if I forget during the demo, please just bring it up again. But that's a really good question for the demonstration. Thanks for asking that one. All right. Oh, the last thing I'll say on coordinate system is, if you do define the coordinate system for the basin model first, and then you load the terrain, if there's a difference between the basin model projection and the terrain's projection, then HMS will automatically reproject the terrain into the basin model's projection. Okay? All right, and then this shows you, this is the very simple process of selecting the terrain model. Like I showed you, you're going to click on the basin model within the Watershed Explorer. You're going to see this component editor that you see on the figure right here. And then what you do is you just select the terrain model. So I'm going to choose NED 10 meters right here. Click the Save Project button, and then you should see the terrain model loaded into the background map, or the basin model map for you. So there's my terrain model. You can edit the draw properties. So if you don't like the way it looks, you can choose a different color ramp or scale to display the terrain model. And then you can also load in other shape files. If you have your national hydrography data set and you want to load in river reaches that you've clipped to the watershed boundary, you can load in those river reaches. If you have precipitation gauges or flow gauges, you can load those shape files as background images or background shape files. Terrain reconditioning. So in HMS, it's called terrain reconditioning. In Geo-HMS, it was called burn streams or build walls. So that's different terminology, but exactly the same thing. You can use your terrain or your national hydrography, river reaches, or watershed boundaries, and you can use those shape files or polylines and polygons to impose information onto the terrain model to force the drainage that you want. And then this is the very simple example that I like to show folks. This is a project I worked on, oh man, maybe 50 years ago, or 15 years ago. And I ran through the automated delineation process in Geo-HMS and then compared those to the published watershed boundaries in the National Hydrography data set. I don't remember the HEC scale that I made the comparison to, but the comparison, so the National Hydrography data set, for some reason I labeled that as NRCS in this figure that I made a long time ago, but let's just assume that the NRCS, those values in red, that's the drainage area from the published information, and then the drainage area for these, for auto, or the black text, that's from the automated delineation. And you can see in some of these areas, there's a good match between automated delineation and those published watershed boundaries. But in others, there's not a good match, right? So like down here, look at the difference between the auto-delineated subbasin boundary and the published boundary. This is one of those examples where if you use the terrain reconditioning tools, you're able to impose that known information, the published boundaries, into the terrain model itself. And then this is how it works. You choose your stream layer. So let's just say I'm representing my stream layer in this simple 2D plot with this dot right here. You choose the number of buffer cells, the smooth drop, and then the sharp drop. In the program here, I've chosen the buffer is 2 cells, so 2 cells to the left and the right of my stream line. The smooth drop is 5 feet, so there should be a 5 foot drop from the terrain that intersects the stream cell down 5 feet. So that's that, and then another 1 foot sharp drop on top of that to represent the actual channel itself. Right, so that's the burn streams part of terrain reconditioning. And you have the same options if you're trying to build walls. So if you have your watershed boundaries or your subbasin boundaries and you're trying to build walls for that published boundary, then you have the same options. You choose the buffer, the smooth drop, and then also the sharp drop. The nice thing about this is, well, if you do have those published watershed boundaries, you do need to specify the stream layer. You can't just impose your watershed boundaries, or you would create like an artificial dam on your terrain model and water would not be able to leave, right? So part of the terrain reconditioning is you choose your boundaries. You also do need to choose the stream so that water can leave that modified terrain. After you have your reconditioned terrain, the next step is you're going to fill those sinks. We have to make sure that water can flow across the land surface, so we're going to create our hydrologically corrected DEM. I'm going to go through this fill sinks process. And then part of the fill sinks tool is going to create a new terrain layer where all those sinks have been filled so that water can move across the terrain. And it's also going to create another layer for you that shows you the locations and how much of the terrain had to be filled in so that it could be hydrologically corrected. And then this next process, pre-process drainage, this is where the program's going to run through those steps where it determines the flow direction. So what's the steepest gradient from cell to cell? So there's your flow direction. And then it's going to create the flow accumulation grid for you. So that's all pre-process drainage is. Flow direction and then flow accumulation. And then the next step is, this is maybe the hardest. This is where some thought needs to be put into it, is define the threshold for the program to define those streams, right? If your threshold is really small, then you're going to have a ton of subbasin elements. If your threshold is large, then you could have just a few subbasin elements. What I like to tell folks is as simple as possible. If you have a watershed with just one flow gauge in it, then consider just one subbasin initially. And if you have a hard time reproducing results, or if you have really good information for why you should subdivide the watershed, then subdivide the watershed more than just one subbasin. But there's a lot of examples that I've seen in the last couple of years where lots of subbasins does not equal a better model. Really what it does is it forces you to justify how you parameterize those many subbasin and reach elements. So watch out for that. But there is flexibility. If you don't like a really highly defined stream network, then you can rerun the tool and increase the stream threshold if you want to. All right. After those streams have been created, then you need to identify the breakpoints, and you need at least one breakpoint. The breakpoint is simply the outlet of the watershed, so you have to have that one. You can add other breakpoints that represent maybe subbasin outlets. You might have locations that have observed stream flow, or maybe you need to know the flow at a specific location because it's the boundary condition for a RAS model, or there's many other reasons why, but you need at least one breakpoint, and that's going to be typically, well, it has to be the outlet of the watershed. Okay, so that's the breakpoint creation tool. And then finally, once you've gone through those steps, this is where you click the option to delineate elements. And part of the process here is you get to choose what type of prefixes you want the program to use. So if you want subbasin 1, subbasin 2, and so on, well, you could choose a prefix of subbasin for your subbasin elements. Reach, junctions as well. Do you want junctions to be inserted into the model? I always choose to insert junctions, but I've noticed there's a lot of people out there that don't like junctions. You don't have to use them. So there's an option there to insert those junctions. And then if you want to convert your breakpoints to a sync element, that option's in there too. And we'll go through these steps in the demonstration here at the end. All right. Once you've run through those initial pre-processing steps, then you get to customize the delineation if you want to. So there's two tools that we'll talk about a little out of order here. The first one being the merge tool. If you want to merge subbasin elements, you can merge those subbasin elements. The only requirement is that those are hydrologically adjacent to one another. All right. You can select those subbasin elements and then come to the GIS menu and choose merge, and then all of them will be merged together. There was a limitation in HMS prior to version 4.9 where you could only merge 2 subbasins at a time, but starting at 4.9 and on, now you can select as many subbasins and choose the merge option as long as those subbasins are hydrologically adjacent to one another. That's a cool option. You can also do it for river reaches as well. So if I were to have multiple subbasins in this area right here and then merge them together, I would still have multiple reaches left behind. You can clean that up. So if you want instead to represent this area with 1 reach segment instead of 4 reach segments, you go through the same type of process. You would select those 4 reach elements, go to the GIS menu, and merge them into 1. That's easy. And then the next thing, the split element. Let's say you ran through those automated delineation steps, but then you realize that you had a gauge at a certain location that wasn't represented as a subbasin outlet. Well, you can always refine the drainage or the element network by selecting a subbasin. So I've selected this subbasin right here. You can choose the split element option here from the GIS menu, zoom in to this area, and click on a cell where you want the program to delineate a new subbasin to, and then connect it to the next downstream junction with a reach element. All right. There is a tricky component with splitting the elements. You need to make sure that you click on part of the stream network. There were limitations in the past where you had to click on the identified stream tool or layer. That's no longer the case. You could click on this blue line that represents the stream network, or let me, oh, sorry. So this shows you the byproduct. You're going to see this, this intermediate window that shows you, this is what the new delineation is going to look like. Do you want to accept it or not? So you have that option right there. Okay, and then what I was getting to just a minute ago, you have to make sure that you click on top of the stream network in order for the delineation to make sense, right? And so what I have here in this figure, This black line, this represents my identified streams layer. So based on my user-defined threshold, this is my stream layer. And then what you see here in the other, I guess, layer, map layer, is the flow accumulation grid. And that flow accumulation grid, that's what I use to see the really detailed stream network, right? And so what I do is I manipulate the draw properties for my flow accumulation grid so that I can see all the cells that have a value of 200, maybe 500 or more, and I can really see that detailed stream network. And then if I need to delineate any area outside of the identified streams, I just turn on flow accumulation and then zoom in so that I make sure that I'm clicking on top of one of those super detailed streams that's represented within the flow accumulation grid. And then the last one here, so GIS data management. This is really important. The GIS process can create tons and tons of data files. And so how HMS manages those is you should notice whenever you create a project in HMS, there's going to be a GIS folder and there's going to be a maps folder. And our recommendation to you all is to put all of your background maps, your shape files, your subbasin polygons, your NHD streamlines, those types of shape files inside of the maps directory. Keep it contained within your project folder. And then as HMS is going through the automated delineation process, it's going to use the GIS folder. And you should notice within the GIS folder, there should be a separate directory for each basin model, and the program stores all of those intermediate flow accumulation, flow direction, all of those files within that GIS directory. And then also within the main project directory, you're going to see what we call the SQLite file. This SQLite file, this is the file that contains all the geographic information for your subbasins, reaches, and other elements in the basin model. In the past, there would only be a .basin file for each basin model in the project. But now, since geographic information is being included, that's going to be stored in the SQLite file. And then the terrain file, this is just a file that maps the different terrain layers that you've added to your HMS project. All right, so that was the delineation part. Let's jump to characteristics. Once you have your model delineated, you can run the subbasin characteristics tool, and you're going to see information like this. You're going to see the longest flow path for each subbasin, the flow path slope. There's also the 1085 flow path, the 1085 slope, and then other types of characteristics that you can get from this tool. And then these characteristics, why are they there? Well, if you have regional regression equations that take this information and estimate model parameters, and you'll see in the tool that I'll show in just a second here, you can take information in this characteristics table and use that to estimate parameters like your time of concentration. So that's subbasin characteristics. You also have your reach characteristics. Not as many, but you have your reach length, your reach slope, relief along the reach length, and then sinuosity. All right. The expression calculator. This is exciting to me as well. Estimating those model parameters from your GIS data. The way that you access the expression calculator is you open up the global editor. And then in the demonstration, I'll show you where to get to the global editor. But the global editor is a tool that's available to you within the basin model to quickly parameterize all the elements that have the same modeling method. For example, the figure on the left, this is my Mod Clark component editor or global editor. There's 3 subbasins that have the Mod Clark method selected, and you should see a table here of time of concentration and storage for each of those 3 subbasins. If I want to use the expression calculator, I click the calculator button right here. And then this is the expression calculator that's going to open up, and you have different options for estimating these parameters. You can click on the stats tab here and use those characteristics that I showed in the previous 2 slides, Or if you have grids that are added to the project, you could reference those grids, and then the program will compute the basin average for you, or the sub-basin average for you. Okay. See, is there a question out there? Okay. All right, and so in this figure right here, I show, here's the expression calculator again. Look at this formula right here. So this is just a simple regression equation that's being used to estimate the time of concentration. Let me just stop here. I'll go to the tutorials and guides. And you can copy and paste. So this is within the estimating parameters with GIS datasets tutorial. And this is the straight up copy of the equation that you could use. There's other regional equations out there, so make sure you find the right regional equation, but this is just an example. You can copy and paste this into the expression calculator for your time of concentration, and you should see the appropriate values based on the different statistics or sub-basin characteristics for your location. And then this next slide, oops. This next slide is going to show the same type of thing, but instead of using the sub-basin characteristics, I have different grids for the green and amped loss method. And this grid right here, it shows the wetting front suction for different soil types. So it's represented as an ASCII grid file. I loaded that into my HMS project. And then once I reference this grid within the expression calculator, the program's going to compute the sub-basin average wetting front suction for me. Right. So let me pause there. Are there any questions about the GIS tools? Because the next topic, we're going to jump into the hypothetical storm. All right. No questions? All right. So the hypothetical storm, as I mentioned earlier, this used to be the SCS storm. Now it's just simply referred to as the hypothetical storm. There's a couple of just general user options now available. You get to choose the temporal pattern. So the storm pattern, that's the first option here. You get to choose if it's a user specified pattern or if you want to use the different SCS storm patterns. So those are hard coded in there currently. You could also create a DSS file with any type of pattern that you're used to using and use that as the user specified pattern. And we'll do that during the demo here in a minute. You get to choose the storm duration. So I chose 24 hours in this example. And then there's different options for the precipitation depth. You can import your precipitation frequency grid into HMS. I think that the classic example right now is you go to the NOAA Atlas 14 website, you would choose the frequency event, the duration that you're interested in, download that ASCII file. You can import that ASCII file into HMS and then reference it right here. So that's what I did. I'm referencing the 1% precipitation frequency grid that I loaded into my project. Then I chose the computation point in the basin model. And then the area reduction method. You get to choose either TP40, that's the classic area reduction curves, or if you have your own area reduction curves, you could specify those as well. And then either you can specify the storm area, or if you have the computation point selected, the program is going to use the storm area or the drainage area at that computation point. For this example, my computation point is the outlet of the subbasin. The program goes to the outlet there. It finds the area. It's going to use that for the area reduction. Okay. For the precipitation depth, if you have a geo-referenced basin model, the program will go to this computation point It's going to find all of the subbasins that are upstream of the computation point. It's going to kind of like merge those together so that you have just one polygon that represents the entire drainage area upstream of that point. And then it intersects that polygon with your precipitation frequency grid and automatically computes the subbasin, or we'll say drainage area, precipitation frequency depth for you. So you no longer have to specify that by hand or process that information in a GIS tool. HMS is going to do that for you. And then part of the message log there at the bottom right, it'll show you this is the computed depth from that precipitation frequency grid. And then this is the area reduced value after the area reduction is applied to it. All right. And so in this figure here, I'm showing, I went to Atlas 14. I downloaded a 1%, so the annual exceedance probability, 1 in 100 probability precipitation frequency grid. The duration is 24 hours. Downloaded that grid to my project or to my computer. And then there's this nice new tool. This is available in version 4.9 of HMS, but it's what we call our precipitation frequency grid importer. And so you reference that ASCII file that you downloaded from the National Weather Service, and then the units or scale factor for that precipitation frequency grid. And then the program will create a copy of that grid, internalize it into the project, and then you will be able to see it under the precipitation frequency grids folder right here. All right. And then this figure here, this shows the temporal pattern. If you want to create your own temporal pattern, maybe you're using those temporal patterns from Atlas 14 for the different storm types, you can use that option. Or if you have your own or additional SCS temporal patterns, you could specify those as percentage curves in HMS and then simply reference those in the hypothetical storm component editor. And then finally here we have our area reduction curve. If you don't want to use TP40, maybe you have regional regression or regional studies that show how storms in the area, how the storm depth is reduced based on storm area, then you could specify that as your own area reduction factor or curve within HMS. And then finally, the bottom figure here, this shows what I was mentioning just a minute ago. So if HMS is computing the basin average depth from that precipitation frequency grid, you're going to see a message that looks like this. So the hypothetical storm depth is 8.677 inches, really exact. We have our upstream storm area right here. And then the area reduced hypothetical storm depth is 8.285. All right. So you'll see that type of information in the message log. Oh, and then finally here's just a figure that kind of introduces or shows the new frequency analysis compute option. This would be used for those cases where maybe you have your 2-year, your 5-year, 10-year, 25, 50, 100, and so on. So you have different frequency events, and you want to organize those in a way so that it's easy to manage the linkage between basin model and MEP model, and then see the computed peak flow frequency curve from those different simulations. So what you want to look into is the new frequency analysis compute option. And whenever you get the slides, I'll post the slides to that website that I showed you. You should see a presentation from a recent webinar that goes into more detail about the frequency analysis compute. All right, I'll pause there before jumping into the basin model report. Let's look at see a question. So yeah, the question from Joe is, if Atlas 14 data is not available, which is not, that's right. In a few states, they haven't updated or created the grids for those states. Can you use NOAA Atlas 2 gridded data sets? Yes, you sure can. So any type of ASCII file or other file types that have those precipitation depths in them, you can use those in HMS. The only thing that I'm not sure of for Atlas 2, so let me back up. whenever you do create a precipitation frequency grid, you have to specify the units and the scale factor. And for the Atlas 14 grids, I guess for compression reasons, to keep the file sizes down, they've multiplied those precipitation depths by 1,000 and converted it to an integer grid, which it makes sense. But you have to make sure that the scale factor here is 1,000 for those Atlas 14 grids. For Atlas 2, I'm not sure what the scale factor is. So you just make sure you get that right in order to use it. Any other questions out there? Oh, yep, got one. In the hypothetical storm model, which user input represents the rainfall distribution data? All right, let's see. So the rainfall distribution data. So is the question, Yasmin, is it about the temporal pattern or the frequency of event? All right, well, the storm pattern here, this is going to be for your temporal pattern. And I'll go into more detail in the demo in just a minute. But yeah, hopefully that'll help when we get to the demo. All right. All right, almost done with the presentation.
Hey, Matt.
Yeah.
Great presentation so far. It's so good to get this directly from the developers of the program. It might be worth mentioning that part of this agreement, you guys are going to begin to work on incorporating some of the distributions that we've developed using Atlas 14 precipitation values. And, so even though now we need to use that user specified option, the time will come where we may be able to have that right in the program. So
right, yeah, that's a really good point, Dan. And that's really something that I think we should talk about more is what's the best approach, right? What's the best approach to keep it general, but also keep the user interface somewhat easily manageable? So if you all have 20 or 40 new temporal patterns that you want to use, do you want a drop-down list with all 20? Or is it better to have maybe a couple of those workshops that we have on the HMS page, and maybe there's different workshops for different areas that already have skeleton projects in them that have those temporal patterns as user specified curves? I don't know. We'll get there. But yeah, there's a lot of, I think there's additional discussion that we need to go through to get to a nice design. Because we want to make sure that it's flexible, right? Because I'm sure you all are going to do more analysis, more study over time. And if a certain time pattern needs to be adjusted, then what's the easiest way, maintenance-wise, for you all to get that information into the software?
Right. Thanks, Matt. Yep. We've got a lot to work on yet. So
yeah,
good in the years ahead. All right. Thank you.
Let's talk about the reports. This might be exciting to you, it might not. The basin or different reporting tools, this has probably been the most requested feature from consultants out there. I get it. I understand why you want to have a report generated by the software, because it's kind of like a summary, right? This is what the user or the modeler defined in the software. But the funding has always been lacking for a reporting tool until recently. We had we have a nice agreement with Maricopa County out in Arizona, and they were really interested in a reporting tool, and they were able to provide funding. And so we have two basic types of reports right now. We have what we call our standard report option here. You get to choose the compute or the simulation type, and then you get to choose how detailed you want the report to be. So if you want to see all the different loss methods within that basin model, and you want to see different tables for those model parameters, then you can turn those on. If you want to see different time series results for the simulation, then you can turn those on as well. So that's what we call our standard basin model report option there. And then this one's kind of neat too. This is the statistical report option. You'll see for all of those locations with observed flow, these are the different model metrics out there. And for now, we've gone ahead and hard-coded the range for good, fair, and not. Let's see, just do a quick mic check. My VPN stopped, and sometimes that causes havoc. David, can you still hear me?
Yes, I can hear you.
All right, thanks. All right, so that's the statistical reports option. But again, you can see this information either in a table or if you want to see it visually across the basin model in the spatial results, that's available too. HMR 52 storm optimization. I know we had some folks from the NRCS out at HEC back in the November of 2019. We all know what happened after November of 2019, but yeah, that was a good opportunity. And I remember back then we did have a little, maybe 30-minute lecture on HMR 52 storm and HMS, and I can't remember if that was something that that you all generally apply on your studies, but I just wanted to mention real quick, there is the option with the HMR 52 storm tool to select it within the optimization trial. And then HMS will move the storm around to maximize either peak reservoir stage, peak inflow to the reservoir, or peak volume. All right, so it's a nice little tool. It's going to move around this, like the storm orientation. So you can see how the storm orientation the storm orientation changes during the optimization. The storm X centroid, or the storm X coordinate, or the storm Y coordinate, and then also the storm area as well. And we even have a workshop for it too. So you can go to the tutorials and guides area, and there is a workshop that shows you how to set up the HMR 52 storm optimization. That's in there. And then what I included on this slide right here, these are what I would say are maybe the best tutorials to take a look at for those different areas that we talked about. So for the GIS related tutorials, there's the top two, GIS parameter estimation. There's one for the hypothetical storm method. Oh, and then I have the link down here for the HMR 52 storm as well. Oh, I see that note, Dan. So NRCS policy, so TR60 does not specify the use of the HMR 52 storm optimization. However, for some planning, some state dam safety offices may require its use. Okay, so it might be valuable to you all, but I wanted to include it because I think it's a really cool capability. All right, so conclusion, the latest release of HMS is 4.9. But if you're interested in some of the newer features, go for it. Version 4.10 beta 2 is on the website. Our target release date is April for version 4.10 final. Documentation is continuously updated. So if you see a boo-boo in the documentation, you can let us know and we'll be able to fix it almost instantly, right? So we'll get that change added, we'll hit the update button, and that documentation should be updated. Or if you all see that it's lacking in some description and that we need to add more description, let us know and we'll get that description added. Our training information, or tech transfer information, is continuously updated as well. So like I mentioned, I'll take the webinar from today, load it on that page so that everybody has access to it. And then the last bullet, again, we'd appreciate any feedback from you all. So from examples that you will have, or like hurdles that you've run into on different modeling studies, if there's ways that we can improve the software or improve the technology transfer material, please let us know. And yeah, if you have any questions during the demonstration, please put them in the chat, or If you want, I'll try to remember to pause after doing so many things to pick up those questions. And just to make sure, David, can you see and hear everything?
Yes, everything is looks good.
Right, cool, thank you. All right, so I don't know if you all go through this too, but I think every 2 to 3 years we get a new computer refresh. And my last computer, it like literally died 2 weeks ago, and it was so slow. Whenever I turned it in, somebody said, "You know what? The battery on your old laptop was bloated. It was like deteriorating," and yeah, it was awful. It was an awful computer, and so I got this new laptop, and it's amazing. It's fast. It's snappy. I can put it in sleep mode, and then it does come back alive after going into sleep mode. And so I'm already spoiled. But I was getting ready for today's talk, and I go to load ArcGIS 10.4, and I had one of those panic moments on Friday afternoon because I didn't have ArcGIS 10.4. It wasn't installed on my new computer. And I went through the process of getting a new Arc version on my computer, and I got Arc Pro. And I don't know if you all have started using it yet. I'm still getting used to it. I'm noticing that the same features are there as the old ArcView or ArcGIS 10.4 version, but they're just in different locations. So I'm a little slow using Arc Pro, but yeah, getting there. For these two examples that I'm going to use, one of the watersheds, I'm going to call it the Sausapuedas Creek watershed, is located out here in California. So it's about, I don't know, 100 miles north west of Los Angeles. So it's a pretty small watershed, 46 square miles. There is some terrain. I believe the terrain goes from, let's just see here. We have 500, 200, 250 feet around the elevation or the subbasin outlet to along the mountains here. We're looking at about 1771 feet. So there's a nice bit of relief in this watershed. And then the other watershed that I have here is located in Tennessee. So let me zoom to that one. So let's see here. It is, so here's Knoxville. So along the Tennessee River here, Knoxville, and just a little bit south in Maryville. There's a watershed there, and we're going to use that one for using the GIS tools to estimate basin model parameters. All right, so those are our two watersheds. So first for Sausapuedas Creek, this is the final product. So let's go through how we get to this basin model configuration here. All right, what I'm going to do first is I'm going to create a brand new basin model. So I go to the components menu, create component, basin model. I'm going to name this one my test basin model. There we go. There's nothing here. It's a brand new empty basin model. The first thing that I like to do is define the terrain data. Here, you could go to the component or the GIS menu and set the coordinate system. But again, my standard workflow is just to choose the terrain data first. There is quite a bit of processing that goes into creating the terrain data. We have some tutorials and guides on that page that I showed that show you how to use QGIS or ArcGIS to merge multiple terrain tiles into one, how to reproject, how to replace missing, how to convert vertical units to feet if you need to. So that's kind of outside of what I'm going to talk about now. What I'm showing is I already have a terrain data set loaded into my HMS project, and it's already been projected, and the vertical units are known, and all of those things. Okay, so I'm going to choose my terrain data set first, and then when I click the Save button, I get that message about the basin model coordinate system, If I choose the skip button right here, the program's going to use the coordinate system from my terrain data set and apply it to the basin model. So I'll do that. There we go. There's the terrain data. And then if I want to view the elevations, then the trick is you have to go to the View menu, Map Layers. If you have the terrain map layer selected here, then you should be able to hover your mouse and see elevations across that terrain layer. Okay. All right. Let's see, Evan's having he's not able to see my screen. Just making sure real quick, other people can see my screen. Is that the case?
Yeah, I can see your screen.
All right. All right, sorry, Evan. Maybe you get off of VPN if you're on VPN. Maybe it's a bandwidth issue. All right. And then the draw properties. If you don't like this color scheme, you can always click on draw properties and choose a different color scheme if you want to. Modify the minimum and maximum values and so on. So there's other options for visualizing the terrain. So we have that. The next step is I'm not going to use the reconditioner. So I'm not going to burn streams or build walls. In this example, I'm just going to jump to pre-processed sinks. So let's remove those low spots in the terrain. And you can see here in the new layer that was created, my sink fill layer, or no, sorry, sink locations layer. Those are all the locations where the program had to fill in the terrain so that water could move across it, right? And I'm going to click on, so sink fill is selected here. And then if I hover my mouse, you can see how many cells, or like the elevation or the elevation differential that had to be filled in for water to move across the terrain. So I'm guessing this is 3 feet, 2 to 3 feet here. We're looking at probably something that's less than 1 along these cells here. Okay, so that's the sink location and the sink fill. The next step that I'm going to run is pre-processed drainage. This is where the flow direction and flow accumulation. So let's look at flow direction first. It's kind of psychedelic, right? You're going to see there's going to be only 8 values represented in this raster data set. And again, each of the values that you see is a flow direction. So let me zoom in. So 5 is going to be a flow direction. There's 3, there's 4, and so on. I'm guessing it's just 1 through 8 would be the different values that we have here. Or yeah. So that's flow direction. It might not mean much to you. I rarely look at flow direction. The one that I'm going to look at most is going to be my flow accumulation grid. There we go, right? And then each of these cells within the flow accumulation grid, they represent how many upstream cells are there, right? So I'm just going to zoom in here. This cell right here has a value of 425,776. That's how many upstream cells there are from that one right there. If we know the cell size, so it's a 10 meter by 10 meter, we can quickly compute the drainage area at each point here. If you want to see more definition within the flow accumulation grid, what I like to do is, oh wow, this has changed a little bit. Classify option or the stretch option. So the max, if you want to see, so with the detailed stream, let's invert it. So here in this example, it should only show me those that are really detailed, right? So those that have a value of, it's not right. There we go. Yeah, there's just different ways to look at it, right? So in this view right here, I'm kind of masking out those that are pretty low, so lower than 200, but then you can see the detailed streams here for those that have values over 200. So there's just different ways of looking at the display properties for the flow accumulation grid. But if I wanted to delineate a new subbasin along this little tributary, I would need to make sure here in a couple of steps that I'm clicking on top of this stream that's represented in the flow accumulation grid. Right? So that's flow accumulation. All right, the next step is identify streams. And we had a question about this earlier. And oops, it looks like I forgot to set the unit system for my basin model. I like the US customary unit system. I'm just used to that. So now I'm going to run that one more time. So GIS identifies streams. There's my stream threshold. Right now it's set to 0.55 square miles. I'm just going to accept the default for now. Okay. All right. And then let me turn off. Okay, yeah. So now you should see here, those streams, they should be initiated once the drainage area crosses over and is larger than 0.55 square miles, right? Let me run through it one more time. This time I'm going to increase, there, I'm going to increase that threshold. So let's go from 0.55, let's go to 2 and see what happens. So you notice that it got a little bit smaller, or the extent of those streams kind of shrunk a bit, right? So I'm going to get a fewer number of subbasins with this larger threshold. Oh, I should talk about too, the file size for the terrain. Let's look at that. That's pretty important. So for my Sausapuedas Creek example, the terrain data layer is only 14 megabytes or so. So it's a pretty small terrain size. One of the things recently we've been trying to stress with modelers is keep the terrain file size relatively small, even if you're looking at really large watersheds. If you're looking at a 5,000 square mile watershed, you can always resample the grid cell size. So maybe 10 meters is not the right cell size because you start getting into gigabyte size terrain files. So maybe you want to resample from 10 meters to 30 meters, maybe 60 meters, right? So go ahead and resample that terrain data layer, but then use the reconditioner and burn in your NHD stream network or add walls based on those HEC-12 delineations so that you can at least impose the drainage network that you need on top of the terrain. But I usually tell folks, try to keep the terrain file size less than 200 megabytes, just so that you can not spend too much time on delineation, because you can get a pretty good delineation with coarser cell sizes. And that's going to free up more time for you to do model calibration or the analysis part of it. So I try to tell folks, keep the terrain file size less than 200 megabytes, if possible. We have examples where we've used 1 gigabyte or 1.3 gigabyte terrain files, and it works just fine. It just takes a long time to get through it. So that's my identified streams layer there. The next thing I'm going to run is the breakpoint manager, right? So I need to define the outlet of my watershed. So let's just assume that my flow gauge for now is going to be right there. So I'm going to click my breakpoint tool right there, the red button. Click on top of the stream that was identified. I'm just going to call this one my outlet. Click the create button. There's the outlet of the watershed. The next step here is delineate elements. I'm going to choose a prefix for now. I'm just going to choose, I want junctions in there, and then I'm going to click the delineate button. All right. And if you look at my new basin model, it looks like there are, oh, wow, 18 subbasins in it. quite a few subbasins, right? And you notice I'm assuming there's only one location with observed flow. So there's going to be a lot of parameterization. This is not a easy parameterization just to generate flow at that outlet down here. All right. The other option is I can merge all of these subbasins together. I can go through the process of selecting subbasins and choosing, like I think I chose a reach. Let me be careful this time. There we go. Merge. Or if I want to start back over and choose a different stream threshold, so let me just do that as well. So identify streams one more time. I'm going to choose a threshold of 15 square miles. All right. And now if I rerun the delineate elements option again, I should have much fewer subbasins the second time. Oh, I just have one. All right. We have a question here from Elizabeth. Can you pick the points where you want subbasins? Yes. Okay, we'll get to that next. Perfect. So that's the merge part. Let's say you only have one subbasin, but have there's a couple of locations in the watershed where you need to provide information, or where the model needs to provide information, right? So maybe there's going to be a RAS model, and the RAS model is going to start right here at this confluence and go downstream to the outlet. You're going to want the boundary conditions in that case, right? What you can do is you would select this subbasin because we want to split this subbasin. And then you would choose GIS, split elements right there. And then I'm going to click on top of that identified streams layer. So I'm going to click right here, click accept. And so now there's this one subbasin upstream. This is going to generate the boundary conditions to the RAS model. Oops. And then there's going to be the secondary subbasin downstream, which would generate the local flows for the RAS model. All right. So does that help answer your question, Elizabeth? All right, perfect. And then the other option I wanted to show too, let's just to say there's maybe an observed flow gauge way up here in the headwaters of this subbasin. All right, so let's just assume there's an observed flow gauge right here along this tributary. And you notice there's no identified streams layer here. Okay. In this case, what you need to do is turn on the flow accumulation grid. I'll do that. There we go. And then follow the same type of steps as before. You select that subbasin, it's highlighted. You go to the GIS menu, choose split element. And then I'm going to click right here on top of my stream, my detailed stream. Oops. There. Hit accept. And now I have that one subbasin element for the area upstream of this gauge. There's a reach that's routing that flow downstream. There's a subbasin for this area, and then another subbasin for this area. So you get to customize the level of detail or the discretization of the basin model. And now I think now is a good time to go into just a little more detail of the question we had earlier. Let's see. There's a rule of thumb for selecting the threshold for the number of subbasins. Really good question. I don't know, I want to hear from you all. What's some modeling practices that you all follow for discretizing? Let's say we're going to discretize this area right here, and there's only observed flow down here at the outlet. Any rules of thumb that you all follow for the number of subbasins? Gauging stations, present or not. So yeah, that's just the one. We just have that one gauging station down here. and from Dan. You all typically deal with small drainage areas. Here's an example. I heard of this on Monday. They decided that that was the requirement. Lots of subbasins equaled better results. Lots of detail, right? And just because of the assumptions that they made, the 1% flow that was generated from that model, from the 4.5 square miles, exceeded reality. It was pretty wild. So you can run into cases, even though you're looking at really small drainage areas, if you have tons of elements, then you could miss representing how water is moving across the watershed. So the rule of thumb, I'll give you my rule of thumb. I like to keep it simple. I mentioned this earlier. If there is only one gauge down here, then I would probably consider representing this area with one subbasin. Okay. And so now HMS automatically computes the drainage area for me. So there's 51.6 square miles right there. All right. Another option is it looks like there's a largish tributary right here. So there's one big tributary there, and then another mediumish tributary here. So maybe I would consider representing this watershed with 3 different subbasins, right? One subbasin here, one here, and then this small local subbasin right there. And again, I would do this if maybe the terrain, right? Maybe the terrain is drastically different here, and I want to capture some of those slopes within the unit hydrograph better with this subbasin versus that subbasin versus this one. Maybe the precipitation is oriented in a way that this sub area receives a lot more precipitation, or the intensities are a lot higher, and I want to capture that in my model. So that might be another consideration for splitting this tributary and that tributary. Okay. Any other comments or questions out there?
So I'm just thinking about, we have watershed tools that are developed for ArcMap already that kind of build a lot of these things, doing the flow accumulation and the infills and everything automatically in ArcMap. Is there any benefit to running from the very beginning through this whole process in HEC-HMS, or can you kind of jump in at any point, you know, already having a flow accumulated and filled DEM and just start with that and run with it? Or is it better just to start at the beginning?
Yeah, for now, I would start from the beginning within HMS and run the fill and flow direction and flow accumulation. We haven't made it flexible enough yet where you could just start in the middle and insert an existing flow direction and flow accumulation grid. You could trick it, right? As long as you knew which files to edit outside of HMS, you could get it in there. But even I would struggle with that at first. So I would caution not to do that approach. But yeah, I haven't mentioned it yet. Maybe now is a good chance. So let me export. So this subbasin right here, I can export the shapefile. So I'm going to export my subbasin layer and just walk through one other scenario. So let's say you did use an external GIS tool and you did run through all the delineation steps outside of HMS. You can always import that existing shapefile. The option here under the GIS menu is import geo-referenced elements. So I'm going to import information in a subbasin shapefile. So let me find that subbasin that I just added. There we go. You choose a name attribute field, and that's what the program uses to name those new elements that are added. It's going to set the projection for me using the projection of that shapefile, and there we go. And technically, this is a geo-referenced element. If you were to look at the spatial coordinates for this subbasin, it's using the same coordinate system as the subbasin that was created in this basin model. So there we go. I can load in my terrain data right here. And then, so even though an external tool was used to process or to delineate the subbasin, you can still use that. And then you could quickly run through, let's just choose pre-processed drainage here. It's going to create those 2 layers for you using the process here in HMS. And then once you have those, the flow direction and flow accumulation layers created, then you could run characteristics. So you can compute those characteristics of the subbasin here. Or if you want to use any of the gridded precipitation or spatial results, you can still utilize that. So like the bottom line here is what I'm trying to get to is, even though you have an existing delineation, you can still use that existing delineation, but then make use of all the other GIS tools that HMS has. Right. There we go. And then the next thing I wanted to show here is under the GIS menu, like I just said, you can export the layers, so you can export those shape files. You can always back up, kind of like what I was showing. If you want to redo, identify streams, or redelineate the elements, you can do that as many times as you need to. The discretization, if you do want to apply your gridded precipitation to this model, then the thing that you have to make sure that you do is under the discretization method right here, you need to choose one of these, either structured, unstructured, or file specified. For now, I'm going to choose the structured option. And then on the discretization tab, I'm going to choose my standard hydrologic grid, 2,000 meters. And then under the GIS tool, choose compute grid cells. Then you have to display them. They have their own separate map layer. I'm going to choose my discretization right here. And so now you can see here's those 2,000 by 2,000 meter grid cells overlaid on top of my watershed. And if you had any radar data or whatever type of boundary conditions, then you could do the computations at the grid cell level if you wanted to. All right, so I'll pause here if there's any other questions out there. Yep, David got that one. So yeah, if you need to model at a smaller scale than 1 square mile, you can totally do that too. So it's up to you. So if you want to delineate really small subbasins, you have that flexibility. As long as the terrain data is available, you can go as small as you need to. It kind of gets back to one of the only limitation I can think of is the simulation time step in HMS goes down to 1 minute. And as long as if you want to have 5 points on the rising limb of your hydrograph, that means as long as the time of concentration is larger than 5 minutes, then I think you could delineate that subbasin within HMS. Okay. Good question from Drew. Does HMS tie easily into the other HEC tools like RAS, WAT, FIA, and ResSim? For sure, yes, it does. HMS writes the results from the simulation to what we call an HEC DSS file, the data storage system. And then it's easy to link the results in those simulation DSS files to other HEC models. So you're able to that data as boundary conditions to ResSim, to RAS, and to other tools. So yeah. So let's jump to parameter estimation. So now we've gone through the steps of delineating a watershed. It's really easy. It's really snappy. I love it. Now we need to estimate some of these model parameters. Like I showed you, if you want to see the subbasin characteristics, you just go to the parameters menu, characteristics, and subbasin. The program will compute those characteristics for you right there. And then if you want to estimate your other parameters like your loss rates or your transform, then what you do is you open up the global editor. But before you do, you need to make sure that you have the method chosen that you want to use. I'm going to make sure in this example to use the Clark unit hydrograph method here. Well, let's choose SES. So the SCS unit hydrograph method is chosen. If I go to the parameters menu, transform SCS unit hydrograph, there's my one subbasin. And you can see the different, let me make this bigger. So the different options you have, so you have the standard peak rate factor of 484, the Delmarva peak rate factor 284, and then lots of other generic peak rate factors that don't get those nice names as standard in Delmarva. They're just 100, 150, 200, and so on. Okay, so I'm going to choose the standard peak rate factor for now. And then for my lag time, all right, if I want to use an equation to estimate the lag time, then I'm going to click the calculator button right here. Here's my expression calculator. And then I'm going to choose the stats tab right here. And this is where you get to build that equation. I'm going to go the easy route for now. And I'm just going to copy this equation right here. Oops. All right, so it's an equation that uses the longest flow path length, the centroidal flow path length, the slope, the 1085 slope, and some powers and coefficients and whatnot. So that's the regression equation. I don't recommend you all use this. It's just an example. I'll click the calculate button here. And there we go. And you know this is not right? It's not 5 minutes. It's supposed to be in hours is the way this equation is set up. But you get the main point. You can use these equations to estimate. All right, so that's cool. That's a step in the right direction. What I want to show is in the next example, let me jump over to what I call the Pistol Creek watershed. So this is another shed that's been delineated using the GIS tools. In this project, what I've done is I've added a curve number grid. All right, this curve number grid, it was created in ArcGIS. I didn't create it in HMS, but this is one of those future areas I would love to collaborate with you all on, is better ways or tools that are integrated into HMS that create these GIS derived data sets easily. All right, so somebody's already gone through the process. It might have been David, gone through the process of taking land use information, soil information, and a lookup table to create this curve number grid for us. Right, if I ID any area here, so these cells here have a curve number of 70.4, 63, and so on. All right, so I have my curve number grid created. I loaded this into my HMS project. So here it is. And then I can open up that calculator that I just showed. So I'm going to go to the parameters menu, loss SES curve number. I forgot to erase it. So let's erase it. There we go. I'm going to click apply it to. Okay. I'm going to click the calculator button there. And the field that I want to estimate, or the parameter I want to estimate, is my curve number. There we go. And then I have the grid tab selected. There's the grid that I have in my project, my Pistol Creek curve number grid. So if I double click on it, what that is going to tell the computer is, hey, or tell HMS, hey, HMS, here's the grid that I want you to use. There's the subbasin polygon. I want you to compute the subbasin average curve number for me. All right. I'll click the calculate button, and there you go. All right. So there's a really easy way of estimating initial model parameters that really exciting to me. I know a lot of folks, they're used to using ArcGIS or QGIS to do this, but as we build out these tools over time, it's just going to make it easier and easier for modelers to estimate model parameters. So there's the parameter estimation part. Any questions out there? All right. All right, let's jump over to the hypothetical storm. All right, so I'm going to create a brand new meteorologic model. You go to the components menu, meteorologic model manager, click the new button. Let's call this one my 1% precip. There we go. And I need to choose a few things. The first thing I need to choose is the precipitation method. It should be the, hypothetical storm. There we go. And then the next thing to do is I need to link this basin model or this meteorologic model with my basin model. So I'm going to link 1% precip to my basin model. There we go. And then go back to the hypothetical storm component editor. So I chose it in the Watershed Explorer. And here's my component editor down here. The different methods. So here's the default methods. I can choose SCS type 1, type 1A, type 2, type 3, or the user specified option. And then there's also an area dependent option. I won't go into too much detail here, but this is a way that you can choose different time patterns, temporal patterns, and associate those with different drainage areas. Okay, but for now, let's just focus on SCS type 1, 2, or 1A, 2, 3, and then the user specified pattern. So if I choose SCS type 1, then you notice the only options that are going to be available to me is I have to define the point depth. So, well, first I need to choose the right unit system again. There we go. Point depth, so I would need to choose something like 8 inches or whatever I've computed outside of HMS as the basin average point depth, and then choose the area reduction method. So I might choose storm or TP40 and then specify the storm area. So maybe it's 20 square miles, okay? That's the options that you get whenever you choose one of these predefined temporal patterns. If you choose the user specified pattern, then you have quite a few more options that you can work with, right? You have the temporal pattern. I already have a temporal pattern set up. So let's go there. So I took this from NOAA Atlas 14. This is the second quartile storms, the 50% pattern. So it looks something like this. So not as intense as those SCS patterns, but again, it's just an example. So I chose that time pattern that I have associated or created in the project. The storm duration, I need that because that time pattern, it's a percent curve, and that you need to define the storm duration so that the program can build the time pattern over that duration that I specify right here. And then the precipitation method, either I can enter the point depth manually, or I can reference a precipitation frequency grid. And let me just go back to ArcGIS, or ArcGIS Pro, as they now call it. And let's go back to the other watershed. There we go. Let's see here, I downloaded from the National Weather Service the 24-hour 100-year depth. So that's that TIFF file right there. And you can see for here in California or in Southern California, wow. So there are some mountains along the coast here. So we're looking at 15 inches is the 24-hour 1% rainfall depth. I would love about 15 inches of rainfall over the next month, not in one day. But yeah, it's pretty dry out here in California right now. But yeah, so you get an idea. So those are the values. And then if you look inside the watershed right here, the depths are probably in the range of lower, here we go, 7.73 inches at the subbasin outlet to along the higher terrain, it's about 9.6, 9.8. Okay, so that's the 1% 24-hour depth. I've loaded that grid into HMS. So I'm referencing it right here. It's a precipitation frequency grid. So it's referencing that ASCII file that was downloaded from the Weather Service, National Weather Service. And then within the hypothetical storm, I'm referencing the grid right here. So there's my 1% precipitation frequency grid. And then you have the option of specifying the computation point or choosing the storm area. You have to choose a computation point if you're using the precipitation frequency grid. And all that means is, so within that basin model, I selected this outlet. So I right click on the outlet and choose, select computation point. So it's kind of like setting those different points to VIP points, right? Those points that might have observed flow, or those points that might have, you need information at those points for maybe downstream models in the analysis. So really, I really think of these computation points as VIP points. So I have that outlet as my computation point, and then within my hypothetical storm, I'm able to choose that location, and then I don't need to define the storm area because the program, again, is going to compute the area automatically for me from that GIS feature. And just for now, I'm going to use the TP40 area reduction curve. The program knows automatically to use the TP40 curve for the 24-hour duration. So that's important. All right. So if I run a simulation with this configuration, what you're going to see in the results, so let me try this. Oops. Let me turn off my surface layer. I must have been playing around with it. There we go. There we go. All right. So you notice that this subbasin is highlighted right here. Since it's highlighted, I was able to click the graph tab, and I can see the hydrograph from that 24-hour 1% rainfall depth. There it is. And then the resulting flow hydrograph right here. And then in the results or the message log, you can see the hypothetical storm depth. So the basin average is 8.677. And the hypothetical storm area, 46.336 square miles. So that's the drainage area for this subbasin. And then the area reduction, 8.285, right? So just for fun, for comparison purposes, let's look at using the SCS time pattern. Does anybody know, just right offhand, what's the right SCS time pattern for Southern California? Is it 1 or 1A, 2 or 3? Nobody knows offhand? Type 1, okay. Thanks, Carl. All right, so that's what I'm gonna do. So I'm gonna modify this other meteorologic model. I'm gonna choose type 1. And then the point depth. So we saw in this previous simulation that I wanna use 8.285. It's already been reduced for me, so I don't need area reduction. And there we go. Now I'm going to configure a different simulation that uses this SCS time pattern, and then we can compare results. So let's create a copy. I'm going to name this one SCS type 1. And then make sure that I'm using the right meteorologic model. There we go. And cross my fingers. Failed. That's what happens when you run off script. Sometimes you get failures. That's okay. We can figure it out. Let me go back to my Meteorologic model. Make sure it's configured. Yes. Okay. Well, when in doubt, you know what to do. Close it down, let it take a break, bring it back up. We're getting closer. There's a bug in there somewhere, right? You all saw me enter a point depth at some point. So not sure what happened, but we overcame it. And now we can compare the hydrograph using the NOAA Atlas 14 pattern for the second quartile storm, 50% versus the SCS type 1 time pattern. So I'm going to go to precipitation here, choose that one. Hold down the control key, choose precipitation from the other simulation. And you see a big difference, right? Wow. Let me change the plot properties. Oops. Right, so for the SCS pattern, type 1, let's change that one to dark blue. There we go. Okay, so by no means am I recommending to use the Atlas 14 time patterns as the default answer, right? I just want to show the differences in different time patterns and how critical they are. And I know you all know this, right? The time pattern for these hypothetical events is just as important as the precipitation depth, because that's how you distribute those smaller durations, or that's how you distribute the precipitation over those smaller durations. And so if you use a time pattern that spreads out the storm and doesn't concentrate the storm, you could get drastically different results. So these are the different precipitation hydrographs with different time patterns. Let's look at how the flow hydrograph changes. So I think you can drag and drop. Let's see if that works. So I'm going to find the computed outflow here, drop it there, and then the computed outflow from the other simulation. Cool. My legend got reverted, but you can kind of see the pattern, right? You can see the difference in these time patterns. The flow, wow, it's more than 25% different in this simple example. So something fun to look at there. Any questions about what I'm doing? Any concerns? All right, check here. All right, so question from Warren. So on the combined hydrograph and hydrograph plot, can the rainfall hydrograph present the rainfall runoff rather than the excess at the axis? Let's see here. So this right here, so this is the combined, or this is what we call the default subbasin plot, right? And we have total precipitation is blue, the losses are red here. Let's see what Warren's asking. If you don't mind unmute Warren and ask your question, that'd help me.
Yeah, am I coming through?
Yep, there you are. Thanks.
Okay, all I'm asking is, see where the red and the blue are on the hydrograph? The red is at the axis. Can you put the runoff at the axis instead? Because that's what's generating the hydrograph. And it'd be
Right.
easier to see. Yeah.
I see. So you're saying it'd be easier to see the excess rainfall or it'd be better to plot the excess rainfall here versus the losses, right?
Yeah, just let the losses go along for the ride
Uh,
rather than the other way around. It's the red and the blue if you just swapped which one's on top and which is on the bottom.
right. Okay.
That's all I'm saying.
Yep, that makes total sense. There are other options here on the results tab. You know, what's funny is my preferences have changed over time, and when I use the software more than I do nowadays, lots of model applications, I would rarely look at the results that are available on the results tab. But now you have things like cumulative well, let me pick a better one. Cumulative precipitation, and then you have cumulative excess here, and then cumulative loss there. So these, I know the line styles kind of stink right now. They're all the same color, but looking at the cumulative plots is helpful sometimes, especially when you're comparing cumulative observed flow and cumulative simulated flow. So let me look at that. I have a good example.
Yeah, and what I'm saying is that default plot would be a lot more useful for me anyway, if it were presented the other way around.
Yep, that makes sense. That makes sense. So here's one way of looking at this is cumulative observed flow and cumulative outflow. So you can get an idea for how well or poor the model does in the total runoff volume in this example. Let me open up the default plot here. So this might help. So this is at a junction element, not at a subbasin element. So you won't see the precipitation hydrograph here. So here's the default plot, observed, and then computed. And then just for fun, I put in this horizontal line that shows you what the peak flow from the USGS gauge was, right? And so you could look at, well, here's the cumulatives, and you notice that the solid blue or solid red, that's from the model, that's my computed outflow. I have quite a bit more volume, and it's on the receding limb of the hydrograph, right? There's just more runoff volume in this example than observed volume. So just different ways of looking at it. One thing I haven't pointed out yet either is HMS, it tracks whether the results are valid or not. And what I mean is if you look at the legend right here, the legend says compute time, data changed, recompute. And what that means is after the last time the simulation was computed, either I or somebody else went in there and modified the basin model or the meteorologic model. And so the results that are displayed right now don't necessarily represent the valid results. And what you'd have to do is just choose the simulation. So I'm looking at my February 2017 simulation, click the compute button, and there we go. The legend should update now, and it's going to show you the last computed time is March 9th at 10:41 and 18 seconds. Okay, so the program does try to keep track of valid results or not, but the program does allow you to display those results even though something has changed behind the scenes. So just be wary of that. I like to tell folks whenever you open a plot or a summary table, so let me open up a summary table. Always make sure and look at the last compute time here, make sure that that information is still valid, that somebody hasn't gone in there and modified the model. So just for fun, I'm gonna go to the basin model. I'm gonna make a super small edit here. I'm gonna change the area from 46.336 to 46.335, hit the Save Project button, and there you go. You notice that it says now data changed, recompute in these results.